Okay, great. So it's a real honor to be asked to speak here about such a grandiose topic as visions of the future of physics. I'm really happy to see young people organizing and trying to do physics in new ways, not just in terms of new ideas about the subject of physics, but also how to organize academic research, which I think could be improved in lots of ways. So we need lots of experiments in how to do that. So let me dive in here. So I'm actually going to start out with a little review of the last century of physics, because I think our views on what to do are still shaped by the history, and we tend to forget sometimes, or not completely accept sometimes, that we're in a very different situation now than our heroes from the 20th century were. Right? A lot of physicists grow up wanting to be like Einstein or Schrödinger or Heisenberg, and while that's a laudable goal, those people were in a specific historical situation which allowed them to be who they were. And we're not in that situation anymore. The 20th century had a huge progress in the search for fundamental laws, and I'll argue that was true up till about 1980, and then it more or less stopped, I will argue. And physicists had also very big responsibilities because they were key to developing nuclear weapons, and the whole history of the move of physicists to the United States away from Germany and the development of nuclear weapons is intimately connected to World War II and the power politics of that era. Yeah. And also the rise of the modern university system, enrolling large numbers of people. In the 21st century, we're in a different situation. I'll argue that we're going to make and are making huge progress in applying fundamental laws of physics, and that we also face huge responsibilities, namely regarding the Anthropocene, the new geological era we find ourselves in. I don't think physicists are responsible for that era, although I guess you could blame the inventor of the steam engine. So I don't think they have unique responsibilities, but I think everybody has responsibilities, and physicists have their own particular ones. So the 20th century was the century of fundamental physics. I mean that in a very technical sense. I mean the search for a small set of universal laws governing the whole physical world. So not everything important in physics is fundamental physics. I don't mean to privilege fundamental physics in terms of importance. I just mean that there's a certain quest people have had for ideally being able to write down, the dream is some equation you could write down on a postcard, that in principle you could derive all the laws of physics from that, although in practice that would not actually be true, because there's so many emergent phenomena. And progress in fundamental physics, however, slowed down after 1980. And I think it's really important to think about that, try to understand why that's going on. So let me just show you a timeline of that. And I'm going to be very focused on the development of the Standard Model and general relativity, since those are our two best fundamental physics models that we have right now. And so in different colors, I'll show you different things. So orange, an exciting color, means experimental discoveries that were accounted for later by various theories. Green means theorists are happy. Those are theoretical predictions that were later confirmed by experiments. So orange makes experimentalists happy, green makes theorists happy. Black were experiments that confirmed theoretical predictions. That it makes both experimentalists and theorists happy, but it's in black because in some sense, it's a little bit less exciting. It's confirmation rather than some real novelty. Of course, it's crucial, but to confirm your predictions, but it's somehow less of a shock. And red is experimental discoveries that are still not fully accounted for by theories. So it's like orange, but it hasn't been accounted for yet. So those are things to really theorists need to think about the most. Okay, I'll do it by 20-year periods, but I have to start in 1897 because that's when electrons were discovered. In 1905, a guy named Einstein predicted the existence of photons. A guy named Einstein predicted in his Brownian motion calculations that matter was made of atoms. Of course, other people had believed that already, but this was more quantitative evidence that the atom theory was true. In 1905, another guy named Einstein unified space and time in the theory of special relativity. So 1905 is Einstein's year. In 1911, the atomic nucleus was discovered. Big shock. That's one of these experimental surprises. In 1915, a guy named Einstein predicted that space-time was curved and that explains gravity. So that's general relativity. And the year afterwards, he predicted that this theory predicts gravitational waves. And in 1919, the bending of space-time by gravity was found by an eclipse observation. It's actually very, very, if you read about the experiment, it's just barely believable, but later on it was confirmed much more thoroughly by better experiments. From 1920 to 1940, the expansion of the universe was predicted by general relativity. Not by Einstein particularly, but by de Sitter, I guess. In 1923, the photon was actually definitively proved to exist. It was actually very hard to convince people that photons existed. In 1926, the expansion of the universe was found by Hubble. In 1927, quantum mechanics was sort of born. I mean, again, it's silly to give a particular year for that, but that's a crucial year when Schrödinger and Heisenberg did some important things. It's hard to summarize quantum mechanics, but I'll just summarize it by saying that the universe was predicted to be all about linear algebra, Hilbert spaces and operators. In 1930, the first neutrino was predicted to exist before it was discovered. In 1932, antimatter was discovered. Sometimes people say that Dirac's theory predicted antimatter, but if you read the history very carefully, you see that people found it on photographic plates. They didn't believe the photographic plates. And then people started, then the theory came along, and then people looked at the photographic plates again and said, oh yeah, we were seeing positrons, we just didn't believe it. So that's a tricky case. In 1932, the neutron was discovered. In 1933, the first evidence for dark matter is discovered. Galactic rotation curves were starting to act funny already way back then. In 1937, the second heavy lepton is discovered, the muon. Big shock. Okay, 1940 to 1960, fewer experimental discoveries, but some huge new theories. So in 1948, approximately, quantum electrodynamics was built, unifying special relativity, electrodynamics, and quantum mechanics. In 1956, the first neutrino, that is the electron neutrino, was actually found. And in 1956, also, the violation of parity symmetry was found. So it was discovered by Madame Wu that right is different from left, a discovery for which she never won a Nobel Prize, alas. In 1960 to 1980, a lot of stuff, maybe this is like the heyday of particle physics. The second neutrino was discovered. That again was a big shock. In 1963, the first three quarks were predicted to exist by Gell-Mann in his eightfold way. In 1964, the violation of CP symmetry is found. So if you switch left and right and also switch matter and antimatter, the laws of physics still change. In 1968, the theory of electromagnetism, I didn't say this right, the theory of electromagnetism and the weak force, the electroweak theory was constructed. And so the W, Z, and Higgs boson were predicted. In 1970, the fourth quark was predicted from some nice theoretical reasons based on the knowledge of the existing three that were known at the time. And in 1973, actually, the fifth and sixth quarks were predicted to account for CP symmetry violation in part. In 1973, the theory of the strong force was assembled, you could say, or put together. And so you might, if you want to think about particles, you could say gluons were predicted to exist. In 1974, the fourth quark was found. In 1977, the fifth quark was found. In 1975, another shock, perhaps less shocking this time, the third heavy lepton is discovered, the tau. Of course, in some ways that's satisfying because that means that there's 3 generations of quarks and also of leptons. But anyway, that hadn't been predicted, I don't think. In 1979, gluons were actually found. And then things begin to slow down, I claim, in 1980. So in 1981, gravitational radiation is actually found. No one was surprised. When I say this, I'm not talking about LIGO. I'm talking about the Hulse-Taylor binary pulsar experiment, showing that these pulsars spiral down just as you predict from emission of gravitational radiation. Of course, LIGO later found gravitational waves passing through Earth, but I argue that was completely unsurprising at that point. The only thing surprising was that people were good enough to be able to actually detect them. In 1984, the W and Z bosons were found. In 1995, the sixth quark was found, thus completing the 3 generations of quarks. In 1998, an experimental surprise, neutrino oscillations are discovered. So I think what I'm referring to, I'm forgetting exactly what made me put this year to it, but maybe experiments about missing neutrinos from the sun. That is not as many electron neutrinos coming from the sun that you'd expect, convince people that something was going on. I forget why I picked this particular year, 1998. In 1998, also really good evidence of the accelerating expansion of the universe is discovered. So this is what we now sometimes call dark energy. What year it was. Okay, and then the last 2 decades, just confirmations of things that were, I claim, completely unsurprising. The third neutrino was found, completing the 3 generations of leptons. So that's the tau neutrino, was found in 2000. In 2012, the Higgs boson was found, completing the standard model. People in the news acted as if that was very exciting, but I would argue that from like a longer point of view, that would be the exact opposite of exciting. It would be exciting if they hadn't found it. So the big challenges that are left on this list, the stuff that's in red, basically, that are the issue of dark matter, the accelerating expansion of the universe. I have not mentioned inflation in my list here. You could put that as an experimental discovery. If you're confident that it's really been discovered, I'll just leave that as a really important question, both whether it exists and even if you're completely convinced that it exists, you have to admit that it's very mysterious exactly the details of it. Neutrino oscillations, perhaps they are explained fine and dandy by the standard model. Sometimes some anomalies seem to show up that question that. Just in the last few weeks or so, some of those anomalies have been perhaps put to bed by a new experiment at Microboom. So maybe there's nothing too mysterious about neutrino oscillations other than the mystery of the standard model. There's a question more for theoretical physicists. Is the standard model mathematically consistent? Actually, there's a lot of evidence that it's not, due to the kind of non-renormalizability arising from the Higgs boson. A fundamental scalar makes your theory become sick at very large, very high energies. And then the $64 million question, for at least for some of us, is reconciling these two best theories we have of the universe, the standard model and general relativity. These are all very famous questions. Maybe the mathematical consistency one is the least famous of the lot, actually. I wouldn't say that's very famous. It should be famous, but the others are all very famous, and I don't have a whole lot of new stuff to say about them. But the interesting thing is how little progress is being made on them, and indeed on fundamental physics in general. Of course, people are doing lots of wonderful theoretical work in subjects like string theory, but none of it is making any really serious experimental predictions. I mean, predictions that you stick to, that you, if they turn out not to come true, you don't say, oh, well, I'll just turn up some constant a little bit, and these particles I was predicting are a little bit heavier than I thought they were. So, I mean, it's easy to make predictions that let you back off that way. But so theoretical work in fundamental physics is not really engaged as much as one would hope with experiment, not at the way it was in the 20th century, let's put it that way. So what should we do about it? Well, one thing I think would be good to do about it is to become very systematic about organizing our knowledge about physics. There's a whole lot of theoretical physics knowledge in the form of folklore and widely believed results, folk theorems in quantum field theory, and so on. And a lot of times people cite these folk theorems without remembering the hypotheses of these folk theorems. And so these things, beliefs sort of settle in as true without, that nobody has ever actually demonstrated. And so I think organizing our knowledge, clarifying our knowledge would be a really useful thing to do at this point, because basically we're faced with a huge jigsaw puzzle with thousands and thousands of pieces. And it's very hard for anyone to even learn what all the pieces are. And progress might have reached the point where further progress is only possible if we get more systematic about the whole enterprise of organizing knowledge in physics and teaching it. Instead of requiring everybody to assemble the jigsaw pieces, puzzle pieces themselves, maybe there should be some nice websites about them, books and websites. But I want to argue for something even more radical, which is, don't be nostalgic. Don't try to relive the glories of the 20th century. We're in a new situation here. If something isn't working well, try something else. That's a general rule in life, of course. But I'm going to boldly argue that that should apply to theoretical physics. And I will argue that today there are actually more exciting things to do than fundamental physics, better things to do than fundamental physics. Most branches of theoretical physics are actually doing quite well because we have these great laws of fundamental physics so far. They're not perfect, but they're great. And we are very far away from really exploiting them to their fullest. So it's a shame to tell students in a way that sorry, don't go into fundamental physics. But that's actually what I do tell students. If they ask me these days, I tell them that there are other better things to do. I imagine that there will be some who don't listen to me, and there will be probably many more who don't bother asking me. And so I'm not afraid that my advice is going to kill off the subject of fundamental physics. But I think that there are too many people chasing after too few results in fundamental physics right now, and that the easy, cool things to do lie elsewhere. So just for example, in condensed matter physics, we can theoretically and experimentally explore all sorts of marvelous things. And there's a wonderful interplay between theory and experiment, which is, of course, what there was in fundamental physics in the 20th century, crosstalk, where people do an experiment, then it changes a theory, people change the theory, then it has an experimental prediction, then they check it, and yep, it's true or not. That's what you want in physics. And in condensed matter physics, we've got it. We can do all sorts of cool things. You can do what you might call artificial special relativity. So here's a graph of the dispersion relation of electrons in some substance. So as a function, it's a planar substance. So they have a momentum in the x direction, a momentum in the y direction, and the energy. And so this is energy as a function of the momentum. And if you look, it's a fancy surface here. You can get all sorts of fancy dispersion relations. In particular, you can get dispersion relations where at certain points, the surface looks very close to a cone. A cone is the dispersion relation that you get for a massless particle in special relativity, right? Where the energy is proportional to the norm of the momentum. So what we've got here is a substance in which electrons act as if they were massless particles in some universe with its own speed of light, which is not the actual speed of light, but some effective speed of light or speed of these massless electrons in this substance. And so you can study experimentally all sorts of nice things. You can study, for example, massless spin 1/2 particles that are Dirac spinners or Weil spinners, which means they have a handedness, or Majorana spinners, which are spinners that are their own antiparticles. All these types of massless spin 1/2 particles that are theoretically allowed, but aren't present in our universe. Once we thought neutrinos were massless, and that's why people thought about all these things. Now we know they're not. They're massless in some pristine state. Still, they acquire mass by interaction with the Higgs. But the point is that you can get just plain old straight massless spin 1/2 particles in these artificial universes, I would like to call them, which are just substances with dispersion relations, and that you can craft. You can make different substances and study different phenomena. You can create artificial universes with, say, 2 time dimensions. So, for example, what do I mean? So what do I mean by that? These are called hyperbolic metamaterials, if you want to type it into Google and learn more about them. So the idea is light in these materials moves in waves that look like this. This is a very familiar form for a wave motion, but the time frequency, or I might call it energy, omega, is some novel, unusual function of the spatial frequencies or spatial momentum. In normal light, omega squared is kx squared plus ky squared plus kz squared. But you can make metamaterials where the dispersion relation is different and has this minus sign in it. And that basically means that you could pop this negative quantity over to the other side, and you'd be getting the behavior that you'd expect for light in a universe with 2 time dimensions, the ones over on the left-hand side, and 2 space dimensions. So you can mathematically study quantum field theory in space-times with more than 1 time dimension. It hasn't been studied a lot because people say, well, come on, that's not the way it is. But in fact, you can make artificial universes where that is where it is. And so you have a nice excuse now for studying that, but you can actually test your theories in the lab. And it goes on and on like that. So condensed matter physics is growing to a very large subject. And you might say approximately that at least this subject includes the experimental and also theoretical study of, well, I'm perhaps exaggerating here, but I'll do it anyway, all possible field theories in all space-time dimensions and signatures, p space dimensions and q time dimensions, where p plus q is less than or equal to 4. So in other words, you can study three-dimensional matter, and we've got one time dimension, but you can study thin films of matter which act effectively two-dimensional, so you can have two space dimensions and one time dimension. You can study wires. People study interesting behavior on wires, and then you have one space and one time dimension. But you can also get, as I just said, more than one time dimension. So you get a large class of field theories that you can write down, and it's really up to conversations between theorists and experimentalists trying to create substances that effectively, approximately realize these field theories, and then study the interesting properties of these materials that can be accomplished. So all sorts of beautiful mechanisms invented in quantum field theory, like the Higgs mechanism, anyons, all sorts of stuff can be studied experimentally in condensed matter physics. And by the way, you're not just limited to the situation where space is Euclidean space. Since you have crystal lattices, you have periodicity, breaking of the Euclidean translational symmetry in various different ways, which leads to a whole new range of effects, some of which are of course completely standard in condensed matter physics, like Brillouin zones, but some of which get really complicated and interesting when you start throwing in all the tricks you can play in condensed matter physics. If you're really interested in that, there's a great paper by Dan Fried and Gregory Moore on that. So each such physical theory has a phase space in the sense of statistical mechanics or thermodynamics. And then there's actually also a space of all these theories. If you want to show off, you can call it like a moduli space of theories. So there's a very large mathematical structure here, which we're nibbling at by doing studies of individual field theories or classes of field theories. And this space is reminiscent of the landscape in string theory, or also what they call the swampland in string theory, which are theories that might not have underlying string theories, but are described by quantum field theories. But unlike the speculations regarding the landscape in string theory, which tend to verge into almost theological or anthropic speculations, this is stuff that's accessible to experiment. And so it's really interesting physics studying this. So a whole lot of work has been done on classifying topological phases in these theories. So phases where you have a mass gap, and so where the zero energy states or you can focus on what's going on with the zero energy states. And in those zero energy states or lowest energy states, nothing interesting at all is happening locally. All that's happening is purely topological, global phenomena. People who haven't studied topological quantum field theory may think it's a very fancy, complicated thing, but I think a better attitude towards it is that it's studying things that are incredibly simple, so simple that you can actually understand them in detail with mathematics, because it's physics where nothing is going on locally. That's very boring. It's so boring locally that you can move on to study the global aspects where the topology comes in. And people are going ahead and bringing more and more sophisticated math into understanding the topological phases in condensed matter physics. It's deeply connected to category theory, for example, modular tensor categories, but also higher categories as you go up to higher dimensional field theories. But that's just the start, because that's just the study of physics where nothing interesting is going on locally. the math of full-fledged quantum field theory is much richer than that. So there's a huge amount of work to be done, and it has the advantage that it's connected to experiment. So there's no shortage of exciting things for theoretical physicists to be doing, okay? You don't need to feel depressed that we haven't found dark matter or something like that. I would just say, focus on doing things that you can do that are exciting. But there's another approach to life, which is not what is fun to do, but what should I be doing? So we could ask, what should we be doing? That's a different type of question. So if you think about what's going on, you have to examine the whole big picture. And the big picture is that we've left the Holocene, the geological era that was rather pompously called the present, and we've entered a new epoch called the Anthropocene, which is defined to be the era when the biosphere is rapidly changing due to human activities. And I want to emphasize that global warming is just part of this process. I hope you've all been reading about the COP26 conference in Glasgow. You see humanity feebly beginning to recognize the fact that we're affecting the atmosphere and that we have to do something about that if we don't want our environment to become unpleasant for us. But I want to really emphasize the next point that people are going to discover, which is that global warming is just one aspect of a much bigger process. Part of what's driving this process, of course, is the human population, which to a zeroth approximation, you could say that there were no people on Earth until now, and now they're an infinite number. That would be a pretty good approximation to this graph, horizontal and then vertical. Of course, that's just an approximation, but you could say that in the last couple thousand years, the whole state of the Earth has changed. And the way that everyone's talking about it right now is that starting in the 1800s, we developed the skill of digging underground, digging up carbon and burning it. And so we have decided to power our civilization by burning carbon. And so once you get a good idea, you do it as much as you can. And so, well, we thought it was a good idea. So we're now burning about, probably by now, this is old, so probably now about like 8 gigatons of carbon a year. That is the largest single human activity in terms of sheer mass, is burning carbon. And so we've bust ourselves out of the Ice Age cycle, where the carbon dioxide concentration went between 200 and 300 parts per million. It is now above 400 million. Again, I can see this graph is old because this line pokes up above the top of the graph now. You can tell you're in trouble when you have a graph of some data that extends back hundreds of thousands of years, and you can, just by glancing at the graph, you can see that the graph is about 20 years old, because the line is poking up above the top now. That's the situation we're in. So we're not going to be having ice ages anymore for hundreds of thousands of years, because we've got way too much carbon dioxide in the air for the next one to happen. Here's just a graph of temperature that again shows this vertical behavior in the present. And here's a graph of the volume of Arctic sea ice in the summer at its minimum point. And you can see that when I was in high school, there was 3 times as much ice as there was in 2018. So again, massive changes in the biosphere and, well, the surface of the Earth in our lifetimes, at least in my lifetime, and certainly in all of your lifetimes, you will see equally dramatic changes. So, but the point is, global warming is just a little fraction of what's going on here. The real issue is that we dominate the biosphere now. For example, here are some really important points. About 1/4 of all chemical energy produced by plants by photosynthesis is now used by humans. The biomass of farmed mammals is 14 times that of wild mammals. So basically the idea of wildlife is basically gone, essentially. The biomass of farmed birds is 2.5 times that of wild birds. So that where birds are doing a little bit better than mammals as far as the wilderness remaining. Populations of large ocean fish have declined 90% since 1950. And the rate of species going extinct is somewhere roughly between 100 and 1,000 times the usual background rate, meaning the rate in the Cenozoic. I mean, of course, it was higher when the asteroid hit to kill off the dinosaurs, but I mean, more recently. So we're causing a mass extinction event. Humans now take more nitrogen from the atmosphere and convert it into nitrates through the Haber process to make fertilizer than all other processes combined. So as you may know, plants work with fungi to take the somewhat inert atmospheric nitrogen and convert it into things like ammonia and nitrates that are biologically active and necessary for formation of proteins. That's a natural process, but Haber invented a process where you could burn fossil fuels and fix nitrogen from the air. And we now use that to power our agriculture, to fertilize. And that's dominating the biosphere now, in the sense that that's more of a big deal than the natural processes. And similarly, 8 to 9 times as much phosphorus is flowing into the oceans than the natural background rate. Phosphorus we dig up from the ground and use it as fertilizer. We are not very good about this, so a lot of it gets washed away into rivers. It then goes into the oceans. It creates algal blooms and thus dead zones in the ocean when the blooms die and organisms eat them. And basically oxygen gets sucked up and fish die in most coastal waters. So basically, we're really radically affecting the chemistry of the biosphere, and we've until very recently we've been doing it in a sort of blithe way where we just go ahead and do it without thinking that we might ever run into any sort of limits on this activity, that it might ever cause any sort of problems. So we obviously have to change our whole attitude towards interaction with the biosphere. We can't keep pretending that we can just do whatever the hell we want and nothing will ever rebound on us. So what should theoretical physicists do? I should add experimental physicists here too. I'm sorry, this talk was once prepared for some audience of theoretical physicists. I've adapted a bit, but I forgot to broaden that out. That's a really hard question. I don't know the answer to that top question. I hope you guys and gals figure out good answers to what should physicists do about this. So here are just some obvious thoughts. Well, maybe later some less obvious thoughts. Like everybody else, we should do our part to curb global warming, right? So there's lots of things that we should be doing. One thing we should do is we should just stop flying to conferences. I know it's fun to sit around and talk to people at coffees. Yes. But come on, let's get serious here. So for example, European Union citizens emit on average 8.4 tons of carbon dioxide per year, at least at last when I was able to get the most recent statistics. Suppose I'd flown from Los Angeles to Berlin for some conference that you had. Suppose you paid me to fly out somewhere around Berlin. I just picked a city. Well, that round trip flight would have cost 3.4 tons of carbon dioxide. So sort of not quite, but almost half the annual carbon budget of an EU citizen, which I should add is higher than that of a typical world citizen, which I should add should be 0, because we have to completely cut carbon emissions down to 0. So it's just an untenable use of, it's just not something we should be doing. One thing we can all do is, this is sort of less specific to physicists, I guess. Physicists are more likely to fly to conferences than typical people, but everybody eats. You can eat less meat. By switching from a high meat diet to a vegan diet, it can cut your carbon dioxide emissions by about 1.5 tons per year. And this doesn't need to be a religious all or nothing kind of thing. You can just eat less. This is sometimes an extremely controversial thing to mention. I only mention it here because I have the bad habit of being honest, that you should at least consider having fewer children or adopting children. Because, for example, there's been a study of this done in the United States. It would vary from country to country. US, of course, has very high carbon emissions, so it would be less somewhere else. But in the US, each new child adds, over their life, 9,400 tons of carbon dioxide into the air. Of course, messing with people's reproduction decisions is a good way to get people really mad at you. But I just would like to raise that as a thing to think about. Okay, but what about physicists in particular? Well, you can learn more about the problems and the solutions and tell everyone. You may think that that's a rather small thing to do because you'd like to do something bigger than just like tell people about things that some other people already know, but I claim that that's not such a small thing, because physicists are much better than average at quantitative reasoning. Simple things like being able to look at a graph and understand it, being able to understand order of magnitude estimates, all sorts of things that are standard in physics training are not at all what most people know how to do. And so you can, just by telling your friends or having a blog and telling the world facts that are known but not adequately explained, you can really help increase people's knowledge of some important issues. You can use your knowledge of physics to actually help solve practical problems. I'll talk a bit more about that too. And crucially, you can be creative and have all sorts of brand new ideas that I can't even imagine. So let me talk a little bit about numbers and quantitative reasoning. So to keep global warming below 2 degrees Celsius by 2100, it's likely that we will need negative carbon emissions. Most of the plans that succeed in keeping it below 2 degrees C have negative carbon emissions after 2060 or 2070 or something. So how in the world do we achieve negative carbon emissions, and how much do we need to achieve? Well, we're putting 38 gigatons of carbon dioxide into the air each year right now. To keep global warming below 2 degrees Celsius by 2100, we'll have to cut carbon emissions to 0 by around 2050. But then after that, we'll actually start needing to be removing 10 gigatons of carbon dioxide from the air, and then ramping that up to double that by 2100. Now, you might decide that this is just hopeless and that this 2 degrees Celsius figure is just not going to be maintained, that we're going to have more global warming. That's quite possible, but we have to at least think about trying to do it. And we have to think about the numbers. So some solutions that people propose when they hear about this problem just aren't big enough. And so this is where having some quantitative skills is really helpful. Let me just pick a random example. This is a sort of silly example, but sometimes when I mention this, some people say like, hey, well, can't you make plastics out of carbon dioxide? You could make plastics from carbon dioxide and suck carbon dioxide out of the air that way and make a product that you could sell so that there'd be an economic reason for doing it. Yeah, it sounds nice. The problem is just the scale. So you just look it up online, you find out that right now we make about 360 megatons of plastic per year. That's a fairly large amount of plastic, but as you notice, it's not nearly enough because we're trying to remove something like 10 gigatons of carbon dioxide from the air each year. So the only way that this could possibly succeed in really fully solving the problem would be to massively ramp up our production of plastics. So some more reasonable solutions are something like this. You could get rid of 10 gigatons of carbon dioxide per year this way, over 10. If I'll distribute my slides, and then you can click on these links and see the evidence for these claims here, but you could get rid of about 1 gigaton per year by planting trees, 1.5 by better management of existing forests, 3 by better agricultural practices, 5.2 by biofuels with carbon capture, although this is a very tricky issue. If you don't do it right, you cause more damage than you prevent, because you do not want to be chopping down forests to turn them into biofuel plantations, for example, which sometimes people actually do. Now, so these are things that are at approximately the right scale, and you'll notice that they all involve plants. Only plants, as far as we know, have the ability to process carbon at the scale sufficient for dealing with the problems that we're causing. So machines that suck carbon dioxide from the air, well, you got to power them somehow. How are you going to power them to the extent that it's worthwhile? Currently, none of that makes sense. Maybe in the future with massive nuclear reactors, you could do enough to make sense. But honestly, let's use biology. Biology has had a lot of practice at sucking carbon from the air. So this is not enough to cancel the 38 gigatons of carbon we're dumping into the air now, right? So we have to reduce emissions, but together with the reducing emissions, we might get negative carbon emissions. But I should warn you that governments are now using dreams of future negative carbon emissions to put off taking action now. A whole bunch of the plans that the folks in COP26 are talking about involve first cutting carbon emissions to 0 by 2050, and then going and doing negative carbon emissions to stay below the 2°C limit. So what about actually using your physics skills, not just your numeracy in explaining these problems, but your physics skills? Well, there are tons of things you can do. I can't really list them all, but for example, condensed matter physics in physical chemistry is important for better batteries, better solar cells, other things like that. Nuclear physics for better fission reactors, better fusion reactors. I think we need to be building more fission reactors. I just noticed that China is launching a huge project to build more fission reactors, which will sell to the world. You can say what you want about that, but I think that's, I wish it was the United States that was doing that. I wish you would wish there was Europe that was doing that. But anyway, that's a way to build. That's a way to get energy without putting carbon into the air. I know people worry about the dangers of fission, but so far fission has saved more lives than it's killed by far, because of it's displaced coal, which is much more deadly. Fluid dynamics and atmospheric physics are very complex, interesting physical problems that are necessary for weather and climate prediction, for understanding geoengineering. As the crisis worsens, people are going to get more and more eager for some geoengineering solution to cool the Earth. And whether or not that's a good idea, it's really important for physicists to study it, to prove that it's a good idea or to prove that it's a bad idea. Because I swear, in another 10 or 20 years, people are going to be clamoring for geoengineering, even if they're appalled by it now. The same people will change their minds once they see what the weather's like in 20 years from now. We also need brand new ideas, crucially. So in general, we've been pretending that the Earth is essentially infinite, our effect on the biosphere is negligible, and that exponential growth is the normal condition, the condition that an economy should aspire to. But acting as if these things are true inevitably brought us to a point where they stopped being true. So now we need to rethink everything about economy and the biosphere. So we have this simplified picture that we often use where we take resources, we produce a product, and then we consume it. That picture neglects waste. There's waste at every stage of this process. And because it neglects waste, the waste builds up, and so it causes trouble. And then we go, oh no, so there's waste building up. There's carbon dioxide in the air. There's pollution in the rivers and so on. As if that wasn't predictable from the very start, we have to get out of that silly attitude of oversimplifying and neglecting waste. But even better than that, it's important to notice that in nature, there's essentially no waste. The stuff that comes out of these processes is a resource for further processes. So take a walk in the woods and you'll see there is not a buildup of waste. Well, there could be a lot of leaves and dead trees lying around, but that is not actually waste. If you break into one of those dead trees, you'll see it's full of organisms happily processing that material. And then you'll see, if you watch long enough, birds eating those organisms and so on. And so there's a wisdom to the natural ecosystem that humans have not yet managed to acquire in our own production methods. So it's been said that to understand ecosystems will be to understand networks. The Earth is a complex network of networks of different kinds, which is very hard to understand, but we need to understand it. So in particular, physicists, I think, should think a lot about non-equilibrium thermodynamics and the physics of networks to really get a handle on what life in the Anthropocene is like. That is, what does it mean to live on a planet where you are responsible for managing that planet? So let me just tell you a little bit at the end here about what this last slide, what I am doing, which I'm not claiming is like what you should be doing, but I just want to let you know, like an example of what someone's doing. So I've been studying networks using category theory, and I've been helping researchers use this mathematics to for better approaches to scientific computation. I put these slides on the web. I will put them on the web or give them to you, and then you can click on these blue things and see what I'm talking about here. So there's a new institute set up by a student of mine called the Topos Institute in Berkeley. It's a mathematics institute, but it's a socially conscious organization focused on certain kinds of uses of mathematics. And it has 3 themes right now: connected intelligence, model-based computing, and networked mathematics. And Evan Patterson is sort of one of the people in the model-based computing side of things. And I've been working with him and also with a group of epidemiologists to use category theory to design software that lets you build quickly adaptable models of infectious disease. We're having meetings trying to build that software, and Evan already has built some of this software, but we want to get it up to the point where epidemiologists can actually use it. The point being that traditional programming is very clunky, and it's hard to like take 2 different models and combine them together, stick them together. And category theory, when translated into code, can actually do that. I got pulled into epidemiology because I found epidemiologists were actually open to this idea. I would have been wanting to do this for something like climate modeling or solving global warming problems, but I haven't bumped into people who have the skills and the desires to do that. I'm no good at programming myself, so you need a team of different people to do this type of thing. And it seems like epidemiology is the place right now. And on the more theoretical side, I'm working with Owen Lynch on the category theoretic foundations of thermodynamics. I think there's a lot to be understood in thermodynamics, and in general, a lot to be understood in what you might call mesoscale physics, not micro and scale physics, not astrophysics, but good old physics of things that are about size of you and me, and that we need to understand that type of physics for understanding the problems that face us here on Earth. And non-equilibrium thermodynamics still poorly understood, and so that's what life is all about. So I'm slowly trying to work my way towards thinking about that. Okay, I'll stop here. Thanks.
Thank you very much.
Sure.